In this section, we're going to talk about the motion of a charge in a field. This is a very important topic, and you're going to have a lot of problems that involve this. Right now, we only have electric fields, but the ideas we introduce now are actually going to be relevant for magnetic fields as well. So, very important section, going to be used a lot, and is actually going to be pretty short, because largely I'm going to tell you you need to go back and review mechanics. So first, we need to remember that electric fields are fundamentally about forces. If I have an electric field at a point, we know that that is going to exert a force when I place a charge there. If it's a positive charge, the direction of the force is the same as the electric field. If it's a negative charge, it's the opposite direction. So the first takeaway here, and this is a very common mistake, is that whatever your electric field is not necessarily the direction of your force. If it's a positive charge, it is. If it's a negative charge, it's the opposite, right? This is a 180-degree difference. So please be careful and always ask yourself, is the charge that is experiencing a force due to the field negative or positive? Next, now that we have a force, we relate it back to acceleration. And we know that acceleration, from Newton's second law, is the force divided by mass. Now remember that technically this should be net force. Now the good news is that as long as the field we're talking about is also the net field, so the total field, this will work. The caveat being if there's gravity or something like that to worry about. Most problems are not going to have gravity as a significant effect. That might be something you want to explicitly call out in your simplification and modeling. Other problems will explicitly include gravity. So do please consider that. But so acceleration is going to be our net force from multiple charges or charge and other types of forces divided by the mass. Then we know that our force was simply Q, the charge of the particle we're talking about, multiplied by the electric field. So now we see that my acceleration is simply the charge times the electric field divided by the mass. Well, acceleration was something we basically spent an entire semester on. So hopefully you remember a little bit about that and can use acceleration then to calculate motion. Now, something you might remember from mechanics is that we talked about acceleration and we also talked about energy. In a few chapters, we will learn how to talk about what happens with charges based on energy, but we haven't done that yet. So until we do that, your calculations in this class should be using acceleration, velocity, position, and time, that approach. Now, one thing to note is that if we have a constant electric field, such that our electric field is not changing, we get a constant acceleration, because mass would not be changing, charge would not be changing, electric field isn't changing. So if we place a charge in a constant electric field, then we have a constant acceleration, and that's where you really get to use the mechanics of kinematics and everything that you learned. Remember that most of the equations that are on the equation sheet and that we used in Physics 202, those were only valid for, in fact, a constant acceleration. So we do really want this to be constant. If you have an electric field that is changing as the particle moves through it, we can't use those same equations. The other thing that I want to point out, and this is going to be a mistake that you probably make, is that the acceleration depends on the mass of your particle. And this is going to be the first time we've really talked about mass in this class, so it can be a little bit tricky and catch you off guard. Electrons and protons do not have the same mass. Positrons and electrons do, but there are lots of particles. Muons would be another one. Muons can be negative or positive. Typically, a standard muon is a negatively charged particle. Those also have a different mass. So be careful because there are going to be problems where you're asked about how different particles will vary. And if it's an electron versus a proton, not only does the sign of your charge flip, but the mass is also quite different. So let's look through some really simple scenarios. So all of these are going to be using parallel plate capacitors to actually create our uniform electric field. Because we have a uniform electric field, we have a constant acceleration. So one situation is that we have our parallel plate capacitor, electric field is to the left. We have an electron very near our negative electrode. We let it go and we ask what happens. If it starts from rest, we know that it is going to accelerate to the right. One of the ways you can think about this is that it's being repelled by the negative charges on this electrode and attracted to the positive charges on this electrode. What you should not do is use Coulomb's law for the forces between point charges here. That's fundamentally not what's happened. How you should do this problem is calculate the electric field in the parallel plate capacitor, find then the force on the electron, convert that into an acceleration using the mass of the electron, and then you can calculate the time that it would take, for instance, to get this distance. So that's one scenario. Now I'm calling this 1D motion because it's starting from rest. We could even start it moving to the left or moving to the right, but velocity and acceleration are actually all on one line. So this is a one-dimensional motion situation. Excitingly, we get to deal with two-dimensional motion situations as well. In this case, our particle begins moving to the right, but then it enters a region of uniform electric field that's downwards. This causes it to deflect and it has an angle. How you need to think about this is fundamentally that it is two-dimensional motion. When we dealt with two-dimensional motion in mechanics, we looked at separately our x component and our y component. So our horizontal component stays the same. It does not experience an acceleration in the horizontal direction. This is also a problem where we would ignore gravity. We would only consider the force from the field itself. So horizontally, there is no acceleration, but vertically we see that there is. But we also see that our initial velocity in the vertical direction is 0. So then you could get your final velocity vector by using this distance to calculate what your final velocity component in y is, and then making this out of your horizontal and vertical components of velocity. So again, this is a two-dimensional problem inherently, and you have to use all of the two-dimensional mechanics that hopefully you still remember. Now, one quick thing to point out here is that you could ask in this problem, what type of particle is it? Well, because it's deflected upwards, the acceleration that it's experiencing is clearly in that direction, opposite of the electric field. Therefore, this must be a negatively charged particle. So again, calculating the sign of charge is something that's important, or remembering it. This is another two-dimensional case where we would say that we're by a single plane of charge. So it's still a uniform electric field, but the form will be slightly different because we only have one plane. And it's launched at an angle, initially a 45-degree angle, and it would travel in a parabola. This is again clearly a negative particle because even though it's launched away from the positive charges, it comes back. And again, we would calculate the field from an infinite plane of charge to do this problem, use that to determine the force downwards and therefore the acceleration downwards, and this ends up looking just like projectile motion, except that your acceleration here is not due to gravity. And again, in a problem like this, we would ignore gravity.